All right, let's get into it. Today, we're cracking open the atom to figure out how nuclear reactors work. How do they take one of the most powerful forces in the universe and turn it into electricity for our homes? It's really a story about a massive atomic-scale domino effect and how we learn to control it with incredible precision. So let's see how that first domino gets tipped and what happens in the incredible cascade that follows.
You know, it all comes back to this. Probably the most famous equation ever written, right? E equals mc squared. But this isn't just some abstract idea. It's a recipe. It tells us that mass itself, the m, is just a super condensed form of energy. And if you can figure out a way to convert a tiny, tiny bit of that mass, you get a truly enormous amount of energy, the E. And that's exactly what a nuclear reactor is built to do.
Okay, so an enormous amount of energy. What does that really mean? Let's try to put the power of just a single one of these nuclear reactions into perspective.
The number is just, well, it's staggering. A single nuclear reaction is about 50 million times more powerful than a single chemical one, like burning a piece of coal. And I want to be clear, that's not 50 times, or even 50,000. It is 50 million times more powerful. This incredible energy density is the whole reason nuclear power is so potent.
And here's where that wild number actually comes from. So you take one carbon atom and burn it. You get about 4 electron volts of energy. Fine. But now, take one uranium-235 atom and split it. That's a process called fission. It releases around 200 million electron volts. That unbelievable difference in the energy you get from just one atomic event, that's the whole secret sauce behind nuclear energy.
So, how do we actually unlock all that energy? Well, it all starts with a process called nuclear fission. You can think of this as us, carefully tipping over that very first domino. So, simply put, fission is just splitting a heavy atom, like uranium, in two. When it splits, the pieces that are left over have just a tiny bit less mass than the original atom. And that missing mass isn't actually gone. Poof! It's been converted directly into pure energy, just like Einstein's equation told us it would. The process is actually pretty elegant. It all kicks off when a single free-flying neutron, bam, slams into a uranium-235 nucleus. This collision makes the whole nucleus wobble and become unstable, and it splits apart into smaller atoms. But here's the crucial part. What else gets released? A big burst of energy, sure, but more importantly, 2 or 3 brand new neutrons. And those little guys are the key to this whole operation.
And this is where the real domino effect kicks in. Those new neutrons that just got released, they're about to start a self-sustaining chain reaction.
Just think about it, right? One falling domino can knock over several more. It's the exact same idea here. The neutrons from that first split fly out and smash into other uranium atoms nearby. Each of those splits then releases even more neutrons, creating this cascading, rapidly growing reaction. Now, to control this whole cascade, engineers live and die by one single critical number, the multiplication factor. We just call it K. K is the average number of neutrons from one split that successfully go on to cause another split. Believe it or not, the entire state of a reactor, it all comes down to this one number.
So if K is less than 1, it means that on average, each split isn't creating enough new splits to keep the reaction going. It's like setting up your dominoes too far apart. One falls, but it can't reach the next one. The chain reaction just stops and everything fizzles out.
Now, if K is greater than 1, you've got the opposite problem. Each split causes more than one new split. The reaction snowballs, growing exponentially and releasing energy at a faster and faster rate. This is exactly what happens in a nuclear bomb, and it's the one thing you absolutely do not want in a power plant.
The sweet spot, the Goldilocks zone, the holy grail for a nuclear reactor, is when K equals exactly 1. We call this a critical state. Here, every single fission event leads to exactly one new fission event. The reaction is perfectly balanced, it sustains itself, producing a steady, predictable, and absolutely massive amount of energy.
And that, right there, is the core challenge of nuclear engineering. How do you build a machine that can hold this incredible atomic balancing act perfectly steady, keeping K at exactly 1 all day, every day?
I mean, that's the multi-billion-dollar question, isn't it? How do you actually design a system that can walk this atomic tightrope, starting the reaction up, holding it right on that knife's edge of criticality, and then shutting it down safely whenever you need to? Well, engineers use two main tools. First, you've got moderators, which is usually just plain old water. Their job is to slow down those superfast neutrons, which, funnily enough, makes them better at causing the next fission. Think of it like getting the dominoes to fall at just the right speed. Second, you have control rods. These are made of materials that act like neutron sponges. By raising or lowering them into the reactor, operators can soak up any excess neutrons they don't need, which lets them fine-tune K and keep it perfectly at 1.
In a real reactor, this is how it all comes together. You're looking at a fuel assembly. See how the fuel pins are arranged in this perfect grid? That lets the water moderator flow all around them, and it gives space for those control rods to slide in and out as needed. The whole thing is a masterclass in engineering, designed to do one thing: maintain that perfect K=1 balance.
All right, so we've gone to all this trouble to create a perfectly controlled, self-sustaining nuclear reaction. What's the payoff? What do we actually do with it?
While the immediate product of all this controlled fission is just heat, an incredible, constant, and powerful source of heat that's generated without releasing a single puff of carbon dioxide. At its very core, a nuclear reactor is really just a very, very sophisticated furnace.
And you know, what's funny is that from here on out, the technology is surprisingly old school. It's almost identical to a coal plant. That intense nuclear heat is used to boil water into high-pressure steam. That steam gets channeled to spin a massive turbine, and that turbine drives a generator to make electricity. It's basically 19th century steam power, just fueled by 21st century physics.
So, when you boil it all down, that's what a nuclear reactor is. It's an incredibly elegant machine, designed to set up, maintain, and control a perfect nuclear domino rally, where each falling piece triggers exactly one more, releasing a steady flow of incredible energy in the process.
And that leaves us with one last massive question. The power is immense, it's carbon-free, but those fission fragments, the atomic leftovers, are highly radioactive. So while the immediate challenge is controlling the reaction, the ultimate challenge is managing its legacy. How we as a